Congratulations! At the end of the last video, you should have acquired your first NMR signal, the free induction decay. It's stored here in the top spin interface under the FID tab, although you also see it in the acquisition window. Let's take a closer look at the proton FID of the sample. On the y-axis, we have intensity. This physically corresponds to the voltage induced in the receiver coil by the precession of the net magnetization of the spin distribution that was temporarily reoriented by the transiently applied RF pulse. Once freed from the influence of the pulse, the observable signal will die off due to relaxation processes. That's this exponential decay of the FID that we observe as a function of time. Time in seconds is our x-axis. And we know from our acquisition parameters, as seen in the last video, that AQ, the acquisition time, was set to 2 seconds. The FID is an interferogram, which reflects the sum of all the peaks and all the troughs of all the individual proton signals that we recorded. Every set of protons with the same chemical environment will have the same precession frequency. And likewise, every set of protons with different chemical environments will have a different precession frequency. Since we expect, based on the label on the NMR tube of this sample, that the clear liquid inside the tube is a mixture of deuterated and protonated chloroform, CdCl3 and CHCl3 respectively, there should only be one proton signal. Its resonance or Larmor frequency corresponds to the effective magnetic field felt by the nucleus. The effective magnetic field is a combination of the static external homogeneous magnetic field of 4.7 Tesla and shielding from the magnetic component of the electron density around the chloroform hydrogen nucleus. So here we should have one frequency that decays exponentially. Let's look. Is it decaying exponentially? If yes, good, we're done. If no, if there's a step function that looks like a box, then we've probably forgot the topspin command RGA to automatically set the receiver gain on the y-axis. Next, we're going to ask, has the signal completely relaxed before we turned off the detector? If not, we're probably truncating the FID. That will also give us a step function that will lead to an undesirable sink function in our spectrum. A good rule of thumb is to have about half of the acquisition time recording noise. This is a compromise where we can quickly estimate an acquisition time, avoid truncation of the FID to have good digital resolution, and not record too much noise that will be folded back into the spectrum. Don't change the acquisition time yet. First, let's check the shimming. For those of you following along the basic instructions, we're still on step number 7D. The time domain, the FID, is a plot of intensity versus time. How do we get our proton NMR spectrum for the frequency domain, which plots intensity versus frequency? We'll request the computer to perform a Fourier transform. We'll go over the NMR processing in detail in the next video. Here, our primary goal and interest is in optimizing the acquisition parameters. Ta-da! The proton NMR spectrum of chloroform. What do we see? 2 peaks. On our x-axis, which physically is energy, and then we divide by Planck's constant to express it as a frequency, appears as ppm. What's ppm? It's a way to normalize the chemical shifts given as an offset from a standard, defined as TMS equal to 0. So that the value will be the same for every spectrometer, regardless of the magnetic field strength. So here we see one signal around 7.25 ppm and the other around 1.5 ppm. What are they? Well, we have a very concise and useful NMR article here from the Journal of Organic Chemistry by Hugo Gottlieb et al. Entitled The NMR Chemical Shifts of Common Laboratory Solvents as Trace Impurities, where Table 1 lists water and chloroform at 1.5 ppm, consistent with the trace amount of water in the NMR sample. Next, let's take a look at the line shape and ask ourselves, how is the shimming? Here's our chloroform peak. Uh-oh, what's this little shoulder? That doesn't look like one peak. Let's check every peak in our spectrum. Here's the water peak. It's broader, but it still has the same hint of the same shoulder on the same side. Remember from our previous video on shimming, that shimming corrects for external magnetic field inhomogeneities, and this will affect every peak in the spectrum in the same way, as a consistent deviation from the expected Lorentzian line shapes across all the lines in the spectrum. To see the effect of the shim gradients on the proton spectrum in real time, we're going to enter Go Setup mode. First, we're going to change D1 to 0 seconds. D1, enter 0 seconds. To enter GS mode, I can right-click on the acquisition window and go into Start GS. That will bring me into this red acquisition window. And we see toggle with this button here, a new spectrum. This is in real time. No data is being stored. Let's look at the lock display window at the same time. That's this orange button right here. I can resize it and move it to the side. I've zoomed in on the chloroform peak. Now we see the inhomogeneity in real time, and here's our lock display. I'm going to shim in real time by pressing Z on the BSMS keyboard and changing the direction. We see an increase, and we see, together with that, the disappearance of the inhomogeneity on the line. That's an improvement in the shim. Let's look back at our FID by toggling with this blue button, and we see the line shape is now much smoother in exponent. Let's undo that change to see the difference on the FID. This was our bad shim, and by changing the Z gradient on the shim, we can see the correction in real time as the FID starts to smooth out and look better. When I'm done, I press standby on the BSMS keypad and I press stop to exit GS mode. On our instructions, we're still following step number 7D. And we're going to define in our acquisition parameters the region of interest for our NMR spectrum. Our default parameters were a spectral width SW of 20 ppm and a center frequency O1P of 5 ppm. That matches our current spectral range from our center frequency 5 ppm plus and minus half of our spectral width, or minus 5 to plus 15 ppm. The default parameters set a large SW to catch any surprises outside the ppm range that I expect. Now that I see what's in my sample, I want to set a more tailored region of interest. For the sake of example, I'll choose from 0 to 14 ppm. What's my SW? The difference between the limits 0 and 14, which is 14 minus 0, which is 14 ppm. I'll change SW to 14 ppm now. SW, enter. SW, enter. 14, enter. We can check in our acquisition parameters. In Hertz, SW is now 2,796. What's our center frequency if we want from 0 to 14 ppm? It's the halfway point. 0 plus half of our SW, 0 plus 7 is 7 ppm, or 14 minus half of our SW, 14 minus 7 is 7 ppm. Halfway is 7 ppm. My center frequency should be 7 ppm. To set the center frequency, or O1P, to 7 ppm, I type O1P, enter, and enter a value of 7, enter. We have now told the computer that our region of interest is from 0 to 14 ppm. I will adjust TD, which is just a number, to get an approximate acquisition time for this sample. Let's say we want 6 seconds. My current acquisition time is 2.9 seconds. Let's double TD. It is currently 16K, where K is 1024. Instead, I'd like it to be twice, or 32K, enter, and it is now changed TD to twice, so my acquisition time is also twice as long. The next parameter to optimize is NS. That's the signal-to-noise ratio of my spectrum, which will increase with the square root of the number of shots. So to double the signal-to-noise ratio of my scout shot, I'll set NS to 4. This increases my signal-to-noise by a factor of 2. NS, 1, is now 4. Let's start the acquisition by pressing play. The first thing you'll notice is that inhomogeneity from our previously required acquisition should now be replaced by a more exponential decay after our shimming. And here's our new acquisition time on our x-axis. Here's a zoom to see the oscillation frequency, which is the difference from the center frequency. The difference is taken after the signal is detected, but before it is digitized. In the next video, we'll go over these topspin buttons up here and learn about spectral processing.